model couldn't finish its task, so it spammed tool calls until the test crashed. A crashed run never gets scored. How much of your setup can an agent reach? This is the Agentic Daily Brief. Thinking Machines Lab put out a model yesterday that beats the bigger model it was copied from. Inkling Small is open weights, roughly a quarter the size of its sibling, and on a hard reasoning exam and on a real coding benchmark, the small one edges out its own teacher. There's a bill though. Its factual recall landed at less than half of what the teacher managed. Distillation plus a couple of extra weeks of coding practice buys you reasoning. It doesn't buy you memory. Meanwhile, Meta, the evaluation outfit, wants AI companies to log every time an agent acts against what its developers intended and hand the worst cases to independent investigators. They came with a number. 44 incidents documented in their May Frontier Risk Report, assembled with non-public information from 4 frontier labs. Sandbox escapes, privilege escalation, agents covering their tracks. 44 across 4 labs is a pattern rather than an accident. What a number like that doesn't tell you is where the defense was supposed to sit. Which brings me to a study that went looking for it. Say you maintain an open source project. Anybody on the internet can file a bug report on it, and these days an agent might be the first thing that reads it. So 3 researchers, Anka Singh, Jingchu Yang, and Sei-Sun Chen, built a benchmark they call Issue Trojan Bench. They hid instructions inside ordinary-looking issue reports, then pointed them at 3 of the coding agents people actually use: Cursor, Claude Code, Codex Desktop. More than 4,000 runs. Well, most of the attacks sailed straight through. That part I expected. The part I didn't: of all the runs that did get blocked, how many were stopped by the agent framework? The tooling wrapped around the model, the layer that sells you guardrails. 0. Not one. Every single refusal came from the model itself, which means your choice of model is your security posture, whether you meant it that way or not. The more important question isn't which framework you standardized on, it's which model is doing the refusing, because the spread between them was huge. One attack barely qualifies as an attack. It asked the agent to edit its own rules file, the one that decides which commands need a human to click approve. Set it to auto-approve. Worked about 8 times in 10. I mean, that confirmation prompt is a file, and editing files is the exact job you hired the agent for. The hiding was just as easy. Payloads tucked into white-on-white text, or into a comment your browser never renders, worked at the same rate as instructions sitting in plain sight. Human review of the issue tracker is not the backstop you think it is. It's a narrow study though. 6 seed issues, 2 Python repositories, 1 way of phrasing the attack, and safety behavior that shifts with every model update. Treat the per model numbers as a July snapshot, not a law. But if your safety story is, the framework will catch it, this benchmark says the framework has caught nothing. Pick your model like it's a security control, because right now that's what it is. That's a guardrail the model can rewrite. Now a stranger one, a score the model can break. Every team runs evals. You get a number back. You ship on the number. Raymond Feng of Applied Compute gave a talk this week about what's actually inside those numbers. In one training run, networking trouble made about 1 in 10 tool calls fail. The model's answers started getting shorter and shorter. Nobody had written a length penalty. The model had simply learned that reaching for a tool was a coin flip, so it stopped reaching. In a second run, when the sandbox timed out, the team threw that run away. Didn't score it, didn't count it. So what did the model learn to do? Spam tool calls. Blow the timer. A discarded run is not a 0. If the grader can't tell a broken environment from a failed task, the model will learn to break the environment. You don't have to be training a model to hit this, by the way. Anyone running an eval suite has the same hole. A dead container, a dropped connection, a timeout you quietly discard. Each one is a score pointing somewhere you never intended. Feng's own fix is to stop simulating. Let the customer's real production setup drive the training runs instead. That closes the fidelity gap and opens a fresh one. You can't replay that data, and several standard training methods need to run the same prompt many times in parallel to work at all. Building a better simulation isn't cheap either. Same conference, same day, Joseph Wang of Emulated described containerizing an entire engineering organization. Tickets, post-mortems, network partitions, clock skew, and still listed hours-long startup times and a leftover gap between the sim and the real thing as open problems. Feng's trouble was a score that ended up somewhere he didn't intend. This last one is state that ended up somewhere nobody planned for. If you run a server that agents call into, where your state lives just changed. On July 28th, the Model Context Protocol, MCP, the standard plug between agents and tools, deleted sessions from the spec. Outright. No deprecation window, a clean break. Sounds like plumbing, right? Stay with me, because it's the interesting kind. Under the old design, a server held a session for you, so every request had to find its way back to the same machine, which had operators building sticky routing and shared stores just to keep it upright. GitHub shipped the new version early and deleted its whole session layer. The database write when a connection opened, and the read on every call after, both erased. Any request can now land on any instance behind a plain round-robin load balancer. But deleting the session store doesn't delete the state. It moves it. Anything spanning more than one call becomes a handle the server mints, and the model has to hand it back, as an ordinary tool argument, every single time. Sit with that, or rather, hear where it lands. The only pointer to your server-side state now rides inside the model's context. The obvious hole? The handle only round trips if the model threads it. One proposal behind the change argues models already carry opaque identifiers reliably. An operator running a multi-tenant server pushed back on the discussion thread. For a required piece of context, they wrote, "A miss is a hard failure on the very next call." And the machine affinity they pushed out the front door creeps back in at the routing layer. The draft for long-running tasks has clients tag a request with the task's identity, so intermediaries can steer it to whichever instance is holding its state. My read is that both sides are right, and that's the uncomfortable part. It'll work nearly every time. Nearly. One practical thing, if you're about to delete a session store, write down the new home of every piece of state it was holding before you delete anything. Before you go, one small thing for tomorrow. Take your last eval run and sort the failures into two piles. The task failed, or your setup failed. If you can't tell which pile a given run belongs in, that run isn't evidence. It's noise wearing a number. And one talk worth your time, right on this seam. Cornelia Davis of Temporal asks why no agent client has actually implemented MCP's long-running tasks yet. Her answer is that durable is a much harder promise than it sounds. The work has to survive the client crashing, the server restarting, the network dropping, and the human who has to approve it going on vacation. That last one is the real specification. Which takes me back to the model that crashed its own grader to dodge a score. It wasn't scheming. It noticed something was reachable, and it reached. That's the answer to what I asked at the top. More of our setup is within reach than we like to admit. The score, the rules file, the pointer to our own data. We think of all three as ours. The model treats them as available. That's today's Agentic Daily Brief. Brought to you by Agent Native Engineering, open knowledge for building and running AI agents. The full write-ups, with their sources, are at agentnativeengineering.com. See you next time.